Hey, welcome to The Explainer. Today, we're going to tackle a really fundamental tool in both math and physics, the cross product. It's this incredible concept that basically lets us invent a new direction right out of thin air. And you really need to get it to understand everything from, say, turning a wrench to how 3D graphics work. So let's start with a puzzle. Imagine you're in 3D space, and you've got two lines, two vectors, pointing in different directions. Now, what if you had to find a third direction? One that's at a perfect 90-degree angle to both of the first two at the exact same time. Sounds like a simple geometry brain teaser, right? But it's actually a problem that engineers and physicists have to solve constantly. Okay, so to even think about this, we have to get our bearings in a three-dimensional world. And we define that world with three standard vectors, I, J, and K. You can think of them as the X, Y, and Z axes. Each one is already perpendicular to the others, and they form this fundamental skeleton of 3D space. This is our starting point. So how do we tackle our puzzle? Well, we're going to need a special kind of mathematical tool, a new type of product that's designed specifically for this one job, to forge that third perpendicular dimension. And that tool is called the cross product. Now, you might have heard of the dot product, which takes two vectors and gives you a single number. The cross product is totally different. You put two vectors in, and you get a brand new vector out. And the most important thing, the whole point really, is that this new vector is guaranteed to be perfectly perpendicular to the two you started with. You know, a really simple way to picture this is like a little factory. Your two input vectors, your two directions, they go in one end. The cross product machine does its thing, and what comes out the other side is a brand new purpose-built vector perfectly engineered to be at a right angle to both of your inputs. Okay, so we get a vector that's perpendicular. But wait a minute, that leaves two options, right? Does it point up or does it point down? To figure that out, we need a simple but really powerful little trick. The answer is literally in the palm of your hand. It's called the right-hand rule. No, seriously. Go ahead and hold up your right hand right now. Point your index finger in the direction of your first vector. Let's say it's I. Then, point your middle finger in the direction of the second vector, J. And bam, just look at your thumb. It's pointing straight up, right in the direction of K. That's it. Your thumb automatically shows you the direction of the cross product vector. And this isn't just some cute party trick. It's a physical mnemonic, a convention that ensures we all get the same result every single time. It's like a built-in compass for vector math. So we've totally nailed down the direction of our new vector. But remember, every vector has two properties, direction and magnitude. You know, its length. So what does the length of this new vector actually mean? Well, it turns out that this length isn't just some random number that pops out of the calculation. It actually encodes some incredibly useful geometric information about the two vectors we started with, and it reveals a really surprising connection. Okay, so let's picture our two original vectors again, u and v. Now, what if we imagine they're the adjacent sides of a shape, and we just complete the figure? They form a parallelogram, right? Just a simple, slanted, four-sided shape. Just keep that image in your head for a second. And here is the truly beautiful part. The length of that new vector we created, the one that's sticking straight out perpendicular to the shape, its magnitude is exactly equal to the area of that parallelogram. It's amazing. A vector's length literally becomes a physical area. It's this perfect, elegant link between algebra and geometry. And this isn't some happy accident. It's baked right into the mathematics. The formula for the magnitude of the cross product is the length of u times the length of v times the sine of the angle between them. And guess what? That is also the exact formula for the area of a parallelogram. The math and the geometry are telling the exact same story. So we know what it is, we know which way it points, and we know what its length represents. Now, let's get our hands dirty and see how we actually calculate it, and more importantly, why we'd even bother. Okay, so if you were to just expand the cross product of two vectors, u and v, into all their component parts, well, you get this. It's a pretty intimidating formula, isn't it? It works, but it's long, it's messy, and it is just begging for you to make a mistake. There has to be a better way. And thankfully, there is. We can arrange everything neatly into a 3x3 matrix like this one.
By calculating what's called its determinant, which is really just a specific recipe for multiplying and subtracting the numbers in this grid, we get our answer. You just put ijk in the first row, then the components of your two vectors. This structure turns a nightmare calculation into a simple, repeatable, and way more elegant pattern.
So why go through all this trouble? Because the cross product is not just some abstract math concept. It describes real, physical phenomena that you can actually feel. And one of the most common, everyday examples is torque. That's the rotational force you apply when you use a wrench. Let's break it down. First, you've got a vector r, which is the lever arm. That's the vector that goes from the center of the bolt out to where your hand is. The second vector, F, is the force you're actually applying with your hand. The cross product of that lever arm and that force gives you a totally new vector, the torque, and it points right along the axis of the bolt. That's the vector that actually makes the thing turn.
All right, to really make sure this all sinks in, let's put the cross product side by side with that other vector operation you probably know, the dot product, because they are two very different tools for two very different jobs.
And wow, the differences are like night and day. The dot product gives you a scalar, just a single number, that tells you how parallel two vectors are. The cross product gives you a whole new vector that is, by its very nature, perpendicular. The dot product is 0 when vectors are perpendicular. The cross product is 0 when they're parallel. They're perfect complements to each other. So there you have it. The cross product is our special, purpose-built tool for creating a third, perpendicular direction from two others, with a length that just so happens to represent the area between them. It shows up everywhere, from the forces in electromagnetism to rendering 3D video games. The real question is, now that you know what you're looking for, where are you going to see it at work next?